All right, in this video, we are going to talk about suggested homework problems from 8.2. I'm going to split this section into two videos because the problems take longer to solve, and I don't want the video to go too long. So first, let's talk about what this formula is and where it comes from. So the formula for integration by parts is the integral of u dv, and it equals to u v minus the integral of v du. So if we look at the product rule for differentiation, and then we take the antiderivative of both sides, we'll get u v is equal to the integral of u dv plus the integral of v du. And if I solve for u dv, that's u v minus the integral of v du is equal to the integral of u dv. So that's where integration by parts comes from, is from the product rule. So that's the answer to question one. It's based on what formula? It is the product rule. Okay. Let's go ahead and look at number 3, using the integration by parts. How can you integrate by parts on an integrand with a single term that does not fit any of the basic integration rules? We are going to let u equal the integrand and dv equal to dx. So for example, if I have the integral of, say, ln of x dx, I don't have an integration rule for ln of x. I have an integration rule, something that turns into ln of x, but not a way to integrate ln of x. We'll be doing that later in either this video or in the next video. So what would I do here? I'd let u be equal to ln of x and dv be equal to dx. I'll go ahead and finish this one up just because this may not be until the next video here. So then I'll set up my integration by parts formula. Integral u dv is equal to u v minus the integral v du. So integral of ln of x dx is equal to u times v is x ln of x minus the integral of v du. Don't forget your dx goes on your du and your dv here. So v du, x over x is 1. So I'll just be left with the dx there. And so integral of ln of x dx would be equal to x ln of x minus x, and don't forget your constant of integration c. There's an example for you of what integration by parts would look like. All right, so how do we know how to choose u and dv? We just kind of talked about it a little bit, that there's going to be some things that we don't have integration formulas for, and those things will have to be u. I'm going to put a u on this side and a dv on this side. I use Liate, but I know that some other people like to say ILATE. Either works because both logs and inverse trig functions are in a place where you can't integrate them. You have to differentiate them. I'll actually go with ILATE. I understand why this is, and I like that just as well or better. So I'll go with this since this seems to be the more popular way to say it. If I say Liate in this video or the next one, you know what I'm saying. But inverse trig functions, logs, algebraic expressions that are in the form of x to the n, trig expressions, sine, cosine, tangent, cotangent, cosecant, secant, those sorts of things, and then exponential. Expressions. So Ilate or you can do Liate, doesn't matter to me. All right, let's go ahead and let's look at number 15 here. So the integral of x e to the 4x dx, I need to choose dv to be my exponential piece of e to the 4x. That has to have the dx with it. U has to be x, so du will be a 1 dx. V is going to be, let me show you this formula, e to the ax dx will always be e to the ax over a. Since I'm doing the generic formula, I'll put plus c there, but we just want the antiderivative. We don't need to put the plus c here. So e to the 4x divided by 4. So integral of u dv is equal to u v minus the integral of v du. So integral of x e to the 4x dx is equal to uv. So 1/4 x e to the 4x minus the integral of v du is 1/4 e to the 4x dx. And then integral of x e to the 4x dx is equal to 1/4 x e to the 4x minus 1/4 of e to the 4x divided by 4 plus c. So integral of x e to the 4x dx is equal to 1/4 of x e to the 4x minus 1/16 e to the 4x plus c. Let's look now at number 19. Integral of t ln of t plus 1 dt. So the log ln of t plus 1 has to be u. So that forces dv to be t dt. du is 1 over t plus 1 dt, and v is 1/2 t squared. So that means the integral of u dv, which is equal to uv minus the integral of v du, is the integral of t ln of t plus 1 dt is equal to 1/2 t squared ln of t plus 1 minus the integral of v du. So 1/2 t squared over t plus 1 dt. Notice that in this integral here, that the degree of the top is greater than or equal to the degree of the bottom, so I'll have to use long division there. I'll go ahead and write that out separately here. So t plus 1 into t squared plus 0t plus 0. T into t squared is t squared, t, change my signs and add, minus 1, negative t, minus 1, change my signs and add, plus 1 over t plus 1. So let me scroll up here. That changes this into the integral of t ln of t plus 1 dt is equal to 1/2 t squared ln of t plus 1 minus 1/2 of the integral of t dt plus 1/2 integral of dt minus 1/2 integral of dt over t plus 1. So that's integral of t ln of t plus 1 is equal to 1/2 t squared ln of t plus 1 minus 1/4 t squared plus 1/2 t minus 1/2 ln of, normally we would put absolute value bars around the t plus 1, but we don't need them this time because of the domain of the original. Let me go back up and show you that because there's an ln of t plus 1 in the original, I know t plus 1 already has to be greater than 0, so I don't need absolute value bars around it. It's implied by the domain. Let's go ahead and look at 23. Integral of x e to the 2x over 2x plus 1 quantity squared dx. Now this one doesn't exactly follow Eilate or Liate, but it follows the ideas here. So I have this negative exponent down here that I need to integrate to get rid of. So this needs to be dv. And that forces everything else to be u. And I'm going to have to use a product rule over here. That's okay. This is -2. So this is going to be v is 2x plus 1 to the -1, and then multiplier of -1. Now I'd normally have to multiply by 2, and then 1/2 on the outside. So I have this multiplier of 1/2 that would come along for balancing out my du. And go ahead and go backwards and check if you need to see that that works out correctly. And then over here, du is derivative of the second part, leaving the first part alone, plus derivative of the first part, leaving the second part alone. Going to factor out our GCF. And then when we write our u dv, we have u v minus the integral of v du. So integral of x e to the 2x over 2x plus 1 quantity squared dx is equal to -1/2 x e to the 2x times 2x plus 1 to the -1st. I'll clean that up in a little bit. Minus the integral of v du, integral e to the 2x dx, because this and this are reciprocals of each other and multiply to give me a 1. So integral of x e to the 2x over 2x plus 1 quantity squared dx, say negative x e to the 2x over 2x plus 1 in the denominator, plus 1/4 e to the 2x plus c, going back to that e to the ax over a rule there. Now I want to make a common denominator here. So let's see, there is a 2 here from that 1/2, so minus 1/2 x e to the 2x over the 2 multiplier of 2x plus 1. Excellent. Let's go ahead and multiply by 2 over 2 to get a 4 in this denominator, and a 2x plus 1 over a 2x plus 1 to get a 2x plus 1 in that denominator. And that gives me integral of x e to the 2x over 2x plus 1 quantity squared dx is equal to a -2x e to the 2x plus 2x e to the 2x plus e to the 2x over 4 times 2x plus 1 plus c. And my final answer for the integral of x e to the 2x over quantity 2x plus 1 squared dx is e to the 2x over 4 times 2x plus 1 plus c. Let's look now at number 27. 27 says x cosecant squared x dx. U will be x and dv will be cosecant squared x. Du is dx and v is equal to a negative cotangent of x. Integral of u dv is equal to uv minus the integral of v du. Integral u dv is equal to uv is a negative x cotangent x minus the integral of v du. So that's a negative cotangent x dx. Couple of formulas that are in your book for cotangent of x. U dv is equal to a negative x cotangent of x. I memorize this as a negative ln of cosecant x plus c, because in my mind, cotangent and cosecant are related to each other, and tangent and secant are related to each other, and cofunctions should have negative rules with the exception of cosine. But that just helps me keep that straight. But if I could bring this -1 up and reciprocate this cosecant, it's just as legitimate to call this integral of x cosecant squared of x dx a negative x cotangent of x plus an ln of the absolute value of sine of x plus c. Don't forget your absolute value bars around your cosecant or around your sine, and both of those are correct answers. Let's look now at number 31. Integral of arc tangent of x dx. So this is one of those examples from before where you have ilate or liate, where the I is a part that you need to differentiate. dv is dx, so it's like that single term integrand that we were talking about in number 3. And so 1 over 1 plus x squared is my derivative of arctangent. V is x. Integral u dv is equal to uv minus the integral of v du. So this is integral of arctangent of x dx is equal to x arctangent of x minus the integral of x over x squared plus 1 dx. I'll complete my u substitution here, 2 1/2. So this is arctangent of x dx is equal to x arctangent of x minus 1/2 ln of, and normally you'd put absolute value bars, but x squared plus 1 is always positive, so I don't need them. All right, we got a big problem coming here, and then this will probably be it for this video, and I'll probably come back and talk about the rest of the problems in another video. So dy dt is equal to t squared over root 3 plus 5t. So I'm going to rewrite as dy is equal to t squared over root 3 plus 5t dt. I'll integrate both sides, and y of t is equal to, and I'll do u and dv, and my dv is going to be this negative exponent piece down here, 3 plus 5t to the negative 1/2 dx, and u is going to be t squared. Du is going to be 2t dt, and v is going to be 3 plus 5t to the positive 1/2 times the reciprocal of that 1/2 is 2, but then I need to divide by the derivative of the inside that wasn't up here because I needed to multiply by 5 on the inside and 1/5 on the outside. So there's my complete v. So This is going to be uv minus the integral of v du. So y of t is equal to uv. So 2/5 t squared times 3 plus 5t to the 1/2 minus the integral of v. I'll pull the 2/5 out, and the 2 will make that 4/5 t, 3 plus 5t to the 1/2 dt. Now, because that square root is out of the denominator, and I could have just done this to start off with, and wouldn't have needed integration by parts. So let's go ahead and let's use integration by parts again just to practice. You can use a u substitution here now and let u be equal to 3 plus 5t, but we could have done that from the beginning if we're going to do that. So let's go ahead and now let u be equal to t and dv be equal to 3 plus 5t to the 1/2 again. dt and du is dt, and v is equal to 3 plus 5t to the 3/2 times 2/3 divided by the integral, or the derivative of the inside here, which wasn't visible. So this is 2/15. Don't forget that multiplier of -4/5 out front. So y of t is equal to 2/5 t squared times 3 plus 5t to the 1/2 minus 4/5 times my u v minus my integral of v du with the new u and v. So y of t is equal to 2/5 t squared 3 plus 5t to the 1/2 minus 4/5 times uv is 2/15 t times 3 plus 5t to the 3/2 minus 4/5 plus, let's see, integral of v is 2/15 3 plus 5t dt. So let's not do that. Minus the integral of v du. So leave that -4/5 out and just write that part. That's good. Let's bring this out. Three plus 5t to the 3/2 dt. Excellent. So now we have y of t is equal to 2/5 t squared 3 plus 5t to the 1/2 minus 8/75 t 3 plus 5t to the 3/2 plus 8/75 integral 3 plus 5t to the 3/2 dt. So y of t is equal to 2/5 t squared 3 plus 5t to the 1/2 minus 8/75 t 3 plus 5t to the 3/2 plus 8/75 3 plus 5t to the 5/2 times 2/5, and then times 1/5 plus c. So we have 75 times 25 is 1875. My denominator that I want to pull out, and I have 2 for my numerator, and I have 3 plus 5t to the 1/2, and so 1875 divided by 5 is 375 t squared minus, and then 1875 divided by 75 times 4 is negative 100 t times 3 plus 5t plus, and then all that came out and 2 came out, and that's 8. 3 plus 5t to the second plus c. So this is y of t is equal to 2 root 3 plus 5t over 1875 times 375t squared minus 300t plus, minus 500t squared plus 8 times 9 plus 30t plus 25t squared plus c. So y of t is equal to 2 root 3 plus 5t over 1875, negative 125t squared minus 300t plus 72 plus 240t plus 200t squared. Yes. Plus c. So y of t is 2 root 3 plus 5t over 1875 times 200 minus 125 is 75t squared. 300 minus 240 is 60, but it's negative. Plus 72 plus c. So those all have a common factor of 3. 1875 divided by 3 is 625. When I pull the 3 out, y of t is equal to 2 root 3 plus 5t over 625 times 75 divided by 3 is 25 t squared. 60 divided by 3 is 20 t. 72 divided by 3 is 24 plus c. All right, I think I'm going to stop there for part 1. I'll come back and pick up with the definite integration problems for part 2, starting with number 43 in the suggested homework. So see you for the next video.